define the PMF using binom package, binom module from static package, SciPy static package. You use binom module that takes two parameters, n equals 10 independent transmissions and P success probability is 0.1. And then we found range, so which is list, range, n plus 1. N plus 1 means, so when you use this command, n plus 1 means you have 0 to 9. It's going to be listed as 0 to 9. And then what you have, if you print the range, and then you use binom dot PMF. This PMF is already defined in the binom module. So it's basically object-oriented programming. You guys took C plus EC 103. So therein it is covered what is this method, binom.pmf. You pass range, you pass n, you pass p, and then you get all the values. And then I ask you to sum all these PMF values. I ask you to sum all these PMF values, and check it is 1. And then I said that I would be giving you 3 points extra credit. So those who wrote this code, most of you actually did, and also some of you did not finish. So sign this paper. I'm going to give you 3 points extra credit. So okay. So again, you will have to type this code, and in the exam, there will be some questions, Python-related questions. So you will have to know all these parameters. For example, what are the parameters that this PMF, binom.pmf takes, for example. So you will have to know this code. So it's a good practice that you write, and you will have to complete an assignment in Python as well. All right, so we went through this discrete random variable as well in our last class, and then we skipped Pascal random variable. We went through Poisson random variable. We went through this Poisson random variable that takes parameter alpha, where alpha is the average number of events. And I do have piece of Python code, fully functional piece of Python code as well. You can see if you just simply run this Python code, you will see similar plots that you see here, PMF. Poisson random variable plots. So very similar. I wrote, as I said, that I generated these plots even later. And then there is one example. I put that example as the homework problem. So you guys should be able to solve. Today we are going to start a new topic called expected value. Expected value. Expected value of a random variable. Expected value of a random variable. You guys already know the word, you guys already know the word average. Here, you guys know what is average. Average of bunch of numbers. For example, 5, 10, 15. You take the average, you sum them up, and you divide it by number of elements, which is basically 10. So you are already familiar with average. Average, when you take average is, in statistics, people call it sample average, which means that you know small portion of data, sample small data, and then you take the average. For example, I take the class average. So I have sample number of students, I take the class average. So class average is based on sample of portion of the data. And what is expected value? That relies on the operator expectation. The operator that is applied to determine the expected value is called expectation. Expectation operator, and it is denoted with E. E, expectation of random variable. This expectation works with probabilities, which means that you don't work with a sample data, you work with infinitely many random experiments. So you see that we learned about actually in your computer experiment you saw, you determine the relative frequency, right? You determine the relative frequency. Relative frequency, what you do, you just put number of experiments, number of trials, and then you determine the relative frequency. And if you increase the relative frequency to n, like n equals, if you increase number of trials to infinity, that relative frequency boils down to probability. Okay? So when you random experiment, when you actually perform infinite number of trials from a random experiment and you determine the probability, you use that probability to determine the expectation, to determine the expected value. So expected value is basically, you can think of this as mean of a population, which means that entire data that we can think of. So there is a difference between average, and expectation. Expectation works with infinitely many number of trials, it works with probability, that determines the probability, and then you take basically average on the data that you get from infinitely many trials. So that's the difference between average and expectation. So in other words, expectation, people also call it mean, and I'm also calling it mean. Mean of a random variable. You know that mean and variance. I'll talk about variance in a moment. And in the book, author has mentioned, author has used the letter M sub x to denote mean, but in most of the other textbook and in my other mathematical book as well. In my other notes, I use the notation mu. It is called mu. The way you pronounce is mu, and in later the command this is the command in case you want to write this symbol in markup. Okay. It is mu sub x to denote the mean. To denote the mean of random variable x. Mean of random variable x is basically you take the expected value of random variable x. In other words, you apply expectation operator on random variable x. And as I said, that when you determine the mean, you are thinking of entire population of a data set. So, and at the trial, in terms of trial, you work with like infinitely many trials. And that way you get the probability, and from the probability you get this PMF. So we already know what is this PMF. PMF of random variable x taking value PMF of random variable x taking value x is basically probability that random variable takes value exactly x. Okay. So if this is your PMF times you take x from the range of x. So you already know, because we are working with a random experiment with infinitely many trials. So therefore you will have random variable x and its corresponding range. Its corresponding range we denoted with s sub x. And you take x1, x2, dotted, I don't know how many values you will have in this range, and you take each of these elements here, and then you basically sum the product of this value times this PMF. If you denote this subscript of these random variables as k, so xk, p sub x, xk. So you can just use this subscript of random variable, elements of the random variable x that are given right here, x1, x2, and so on. So these are just some notations, and I'm going to give you an example in a moment. The other important property of this expectation is that expectation, even though number of trials could be infinity, but the expectation has to be finite. It cannot be infinity. Expectation has to be a finite value, a simple number. So that's why this expectation, this is absolute value. This random number can take positive or negative number. Once you have the expected operator, and you sum them up, it has to be less than infinity, which means that this quantity has to be finite. Very important. So that's why I wrote all caps, finite. Now I have drawn these two subfigures here for random variable x, random variable y. Expectation operator gives some hints about the data, and it's usually, you know. So, for example, you have bunch of data here. The expectation, if you apply, if you collect bunch of data, xi, this is I equals 1, I equals 2, I equals 3, and so on. Bunch of data I collected, I generated 150 using random function from SciPy. Okay, 150 data, and then you see that expectation operator is about 5. Expectation operator on this random variable is about 5. And here I have another random variable here. The expectation operator on random variable y gives about 0. So this is one mean. This is another mean. Okay. So now let's go through one example. I have adapted this example from example 3.1 of our textbook. So let x be the number of heads in three tosses of a fair coin. Okay, guys, I'm asking here. The keyword here is fair coin. Find expected value of random variable x in terms of p. Okay. In terms of p, where p can take any value from 0 to 1. P is the probability of observing a head, which means success probability. Now you tell me what sort of random variable it is. Is it a binomial random variable? Is it a Poisson random variable? Is it a Bernoulli random variable? Is it a geometric random variable? Yes.
I think it's a binomial.
Binomial random variable. Why? Very good. Why? It's because these three classes, you know the total number of classes. Okay? You know the total number of classes. So it's a binomial random variable solution. You can straight line solution. So x is a binomial random variable with parameter. Binomial random variable takes how many parameters? 2 parameters. It's the total number of trials, which is 3, and the success probability. Okay? What is the success probability here? 0.5. Because I said that it is a fair point. 0.5 or 1. There is a reason why I'm writing 1. Okay. So this is your n, and this is your p. P equals 1/2, n equals. It's a binomial random variable. Now you tell me what is the range of this random variable. I don't know to do it. What is the range of this random variable, guys?
0, 1, 2, 3.
0, 1, 2, 3. So this is the range of binomial random variable. Now we need to find what is expected value of x in terms of p. First find in terms of p. So expected value of x. Now look guys, the formula, see how I make use of this formula. Look at this formula. So expected value of x is, you take summation, you take an element from, you take an element from the range, and whatever element you take, you put it right here, you multiply with PMF of random variable x taking value x. And this is your PMF. I did not write down the PMF here. So PMF, because you know the binomial, you know the random variable x is a binomial random variable, therefore PMF of this binomial random variable, I denoted with p sub x, comma x, which is by definition probability that x takes exactly value x, is, what is the PMF of a binomial random variable, guys? Do you remember? It's combination n,
P,
n,
N, P,
actually, just to be consistent, guys. So here I wrote x, because
Okay.
I'm multiplying x. So x is the number of successes, okay? So we have x, and then
X,
p to the x, q to the n minus x, okay? Where q equals 1 minus p. Okay. So now, look how you write it. It is, you take one element, 0, 0 times this PMF is going to be 0. Anyway. Now we take another element, 1. So 1 times PMF of random variable x taking value 1, plus 2 times PMF of random variable x taking value 2, plus 3 times PMF of random variable x taking value 3. Yeah. So this is the notation, that's how you expand. Now 1 times PMF of random variable, binomial random variable x taking value 1, you straight use this one, which is 1, actually n equals 3, 1, p to the 1, and 1 minus p, which is q to the n minus 1, which means 3 minus 1 is 2. So now plus 2, so here you have 2, 3, 2, p to the 2 is squared, and then 1 minus p to the 3 minus 2, which means 1, plus 3 times 3, 3, p to the 3, 1 minus p to the 3 minus 3 is 0. So here you have 3, combination 3, 1. What is this? Yes, if you apply the formula, factorial 3 over factorial 1 over factorial 2. So it is going to be 3. So 3 p 1 minus p squared plus 2 times 3, 2. So factorial 3 over factorial 2 times factorial 1. It is going to be 2 times 3. And then you have p squared, and here you have 1 minus p plus 3 times factorial 3 over factorial 3 times factorial 0. It is going to be 1. So it is going to be, and 1 minus p to the 0 is 1. You are left with pq. So I am going to just move on to next page. So I'm finding expectation of random variable x, which is 3p. You have 3p everywhere. So you factor out 3p. So you are left with 1 minus p squared, which means that 1 minus 2p plus p squared, plus you took 3p out, so 2 you have 2p here, 2p, 2p minus 2p, 2p squared. Plus, you took 3p out, so it's p squared. So this p squared, 2p squared, this 2p squared disappear. Plus 2p minus 2p disappear, you are left with 3p. So expectation of x is 3p. So it is in terms of, I said in the question, I said that it is in terms of p, so this is basically the answer. But if I did not say that right in terms of p, and because you are given the pair point, because point is pair, so you have p equals 1/2. So therefore expected value of random variable x, which is a binomial random variable, is basically 1/2. 3 times 1/2 is 1.5. Okay, so that's how. Now, the key thing to remember. So I went through one numerical example, but if you know this is something, if you know x is a binomial random variable, if you know x is a binomial random variable with parameter n, which is the total number of trials, and p is the success probability. So therefore, you know s sub x range, you know it is 0, 1, 2, dotted, dotted, n. So this is your range. Okay. So you found range, and you already determined that x is a binomial random variable. You can directly write expected value of random variable. What is that? Look at the previous example. This 3, do you know what this 3 is? This 3 is basically 3 clauses, total number of clauses. So this 3 is that n, and this p is basically the parameter that you are working with for binomial random. P is the success probability. So it is 3p. And if you have n number of trials, then it is going to be n. Okay? So you can directly write the formula here. Okay? So for binomial random variable, expected value is basically n. So you don't have to go through all these expansion and everything. So you know what to do, but this is basically the formula. Okay, so there is another random variable, geometric random variable. We actually defined what is geometric random variable. So I want to find the mean of geometric random variable. In the exam, I may not mention that it is a geometric random variable. By looking at this random experiment, you should be able to determine whether it is binomial random variable, whether it is binary random variable, whether it is geometric random variable or Poisson random variable. So let x be the number of bytes in a message, and suppose that x has a geometric distribution. So in this example, it's already said that it's a geometric distribution with parameter p. Okay, find the mean of random variable x. So given solution, given x is a geometric random variable with parameter p, where p is the success probability. P is the success probability that a message of certain number of bytes has been arrived. Now x is a geometric random variable. What is the range? You remember the range of geometric random variable x. Range of geometric random variable x, we denoted with s sub x, is basically we can have 1 byte, 2 byte, 3 bytes, it's number of bytes, 4 bytes, until you keep sending message this byte until you receive the character. So this is basically the range. Now, to determine the mean, we need to find, to determine mean, we need PMF. So PMF of geometric random variable x, taking value, let's say uppercase, lowercase, just to distinguish, I denoted with k. Taking value k, which is by definition that probability that your random variable x takes value exactly k. And it is, you remember the PMF of a geometric random variable, it is p times 1 minus p to the k minus 1. So for k equals 1, 2, and so on. So that's the PMF of a geometric random variable. Now we know what is the range. We know what sort of random variable it is. Therefore, we know the range and we know the PMF. It's a piece of cake to find. It's a piece of cake to find expected value. So expected value. Expected value, in other words, we want to find mean of random variable x, which is basically expectation of random variable x, and sum k takes value from s sub x, k times PMF of random variable x taking value, which is basically, and k basically starts from 1, 2, 3, 4, and so on. So you can simply write k equals 1 to infinity, and then you have k times PMF of geometric random variable x is p times 1 minus p to the k minus 1. So, the mean or expectation, mean or expectation of random variable x is basically, you can take p out of the way. This p out of the way, because this summation index, p does not contain this summation index. This p does not contain this summation index k. So you can take p out of the summation. So you have k equals 1 to infinity, and you have this k times 1 minus p to the k minus 1. And I am going to write down, I'm going to use different color now because I will be using some background notation. So just you see that q, I'm going to denote q with 1 minus p. Okay. Q with 1 minus p. Now guys, look. Again, I'm going back to geometric series. So I said that p has to be between 0 and 1. Therefore, q has to be between 0 and 1, not 0, not 1. P is between 0 and 1, not including 0, not including 1. Therefore, q has to be between 0 and 1. So in geometric series, we can write 1 over 1 minus q is basically one plus q squared plus dotted and so on. Okay. Here you can write it as summation k equals 0. Remember guys, k equals 0, not k equals 1. I'm writing k equals 0. K equals 0 to infinity q to the k. So this summation I can write it in this form. K equals 0 to infinity q to the k. If you have this form, I'm going to take the derivative with respect to q. Take derivative with respect to q. d over dq, you take the derivative 1 over 1 minus q, and you take the derivative both sides. d over dq summation k equals 0 to infinity q to the k. Can anybody tell me what is the d over dq 1 over? What is the derivative of 1 over 1 minus q with respect to q? You remember from Calc 1? It is 1 over 1 minus q squared. So this is the derivative of 1 over 1 minus q. And then d over dq, here you have q. So therefore this derivative operator, you can just push it inside this summation. So if you take the derivative q to the k, so k is the power, so therefore you can bring k out, and then you have summation. No, you can directly write derivative operator is inside. So therefore k equals 0 to infinity. You can bring k is the power k, q to the k minus 1. Okay. So here you see when k equals 0, 0 times this quantity is going to be 0. So therefore you can omit k equals 0. So now summation, it is same as summation k equals 1 to infinity. So you can write k, q to the k minus 1. So this is exactly same as your 1 over 1 minus q to the square. Okay? So I am going to go back to my black ink. Here I'm going to write p. Now summation k equals 1 to infinity k 1 minus p, I'm going to write it q to the k minus 1. So we have p. Now do you see k equals 1 to infinity k q to the k minus 1. Do you see the similarity here? Now this infinite summation boils down to a finite number, which is 1 over 1 minus q to the square. Okay? So this infinite summation converges to a finite number with certain value of q. So I can simply write p over 1 over 1 minus q square. So which is p times 1 over 1 minus q is your p squared. So p squared disappears, so it is 1 over q. So therefore, the expectation, which is the mean of geometric random variable x, is simply 1 over p. So it's very easy. So the mean of a geometric random variable is 1 over p. So if you You can read this as a formula, guys. If I ask you to derive, most likely I will give you some parameters, okay? If I ask you to derive, then derive, but if I don't ask you to derive, you can directly use this formula and solve the problem. So, as long as you know how we came up with the mean of a geometric random variable, that's fine. So you can, if you identify that it's a geometric random variable, you can simply write the mean of the geometric variable. All right. So here, you see a piece of Python code right here. So you can import from this statistics package, SciPy statistics package, you can import geom directly. And this is the success probability P equals 0.2. Now, you can directly write mean, you can directly determine the mean of a geometric random variable using geom.mean, and this is your P, your success probability. Directly you can write. Okay. So what is the mean of a if you know that your random experiment consists of a geometric random variable, you can directly determine the mean using this package. So you know what is geometric random variable, you know what is mean, you know the math behind it, you now have the background, you can directly utilize the technology to determine the mean. Okay, so now we are moving to a more complex scenario. Here, I am going to use not only x, I'm going to use another random variable, which is a function of another random variable. So z is a function of another random variable. Let x, g of x be a function of discrete random variable x with range. So you know the range of x. You know the range of random variable x, and you know, so here what is known? X, random variable type, is known. Range, known. And PMF of random variable x, taking value x, known. So these quantities are known. Given this quantity, and also the other thing, important thing, g of x, this function is also known. These quantities are known. If you know this quantity, then I just want you to find, then we want to find the range of random variable z, PMF of random variable z, and then we want to find the expectation of random variable z. So here, problem here is that you are given this function of the random variable. So you want to find the mean, PMF and mean of a random variable that is a function of another random variable. Here, g of x, it is known. And the statistics of x is also known, which means that a type of random variable x is known, and you know the range of random variable x, you know the PMF of random variable x, you know the function g of x. All what you need to know is what is this, what is the PMF of random variable z, and what is the expectation of random variable z. And this is basically the formula. There are two different ways. So one way, you take each element of x, and it is this formula, guys. You are going to utilize this formula directly in your computer experiment, computer assembly. So this is the formula that you will be using. You can use this formula, or you can use this formula, because I said alternatively. So whichever you want. So the way to determine the PMF from random variable is you take each value from this range x, and you pass this value, this element to this function, you get this z. Okay? And for the same z, you can have multiple x's, multiple elements from range x to give the same z. In that case, you apply this summation. And this is known. You apply this summation. And then once you know the z for each z, it's a piece of cake that you find this summation. Z and PML for random variables is getting the z. Alternatively, you can directly use this formula. So in that case, you don't have to worry about finding PMF first. So you can directly find the expectation of z without determining the PMF of the random variable, which is basically you just take each element from x and you pass this element to g of x, which is known. So all these quantities are there. So I'm going to utilize this formula, these two formulas, one of these formulas. Actually, you can use any of these formulas to solve this example. Here, this example, look. This example, you know that x be a noise voltage that is uniformly distributed. Okay, you know that x now solution. You now know what type of random variable x is. So it is a uniform random variable, and uniform random variable takes upper limit and lower limit. So this is your upper limit and this is your lower limit. And this is lower limit. Okay? So you now know it's a uniform random variable, and the PMF is also given. S sub x, range is also given. Range is -3, -1, +1, +3. So this range is given. The PMF of random variable x is also given for all. So this is for all. You guys know, I did mention what this thing is, right? So it's called for all. For all. For all x from the range. That's it. Now, I'm going to use this formula. Expected value of z. Actually, there is another coil or device. So therefore, z, which is g of x, is basically x squared. This is given. Now I can directly use the formula. Expected value of z, in other words, expectation of z, it is denoted with mu sub z, is basically summation. You take x from the range s sub x, you pass this to this function, and then you have PMF of random variable x taking variables. Okay? So now you take x, so it is going to be, guys, x, you take x is -3. So -3 squared is going to be 9. Actually, write one more line. X can take any value from -3, -1, +1, +3, and it is x squared, and then it is times 1/4. PMF of x for all values of x is 1/4. So now it is 9 times 1/4 plus 1 times 1 times 1/4 plus 1 times 1/4, 9 times 1 over 4. Can you tell me what it is? How much is it?
20, 24, so 5.
It is going to be 5, yes. So the expectation of G is 5. So this is the final answer. And I have put some relevant examples. I put some relevant examples, relevant problems in the homework. So you just follow exactly the same procedure. And to my grader, I'm going to give these both formulas to my grader so that he knows that any of utilizing any of these formulas should be fine. Yeah, that concludes my today's lecture. So I will just need 10 to 15 minutes to finish this chapter.